today we're going to talk about routing. Routing is about computing the path. So it means that each router needs to forward the packet following a path. So how do we compute this path? All right. So to do the path computation or selection, I like to do selection because this is really what we're doing here. We may doing regarding using two different algorithms. So you probably already heard about those algorithms, which is the Bellman-Ford and the Dijkstra algorithm. And each of them use different criteria. And when it's the Bellman-Ford, usually we count the number of hops, number of routers in order to reach the destination. So the selection will be based on that distance. When we use Dijkstra, in that case, there's a cost for each link. We sum the links, the weights, the cost of those links, and we take this as a distance. So the most important, because we are networking, is understand what's going to happen when we have a topology change, because running the algorithm itself is pretty standard. But because we are in networking, we have multiple things that we need to worry about here. First, how do we learn the topology? Then, how do we keep it updated? Such as whenever there's a change in the topology, we may update the path as well, right? So how does it happen? And to understand this, so the algorithms are one thing. And on top of this, the protocol. So we're going to understand how the protocols are different from the algorithms. But in our case, we're going to be much more concerned regarding the protocols rather than the algorithm. Because once again, the algorithm, you expect as an assumption that you know the topology of the network. But routers, they don't know the topology. They don't have the graph. So first, I need to learn about the topology. And that is what's the most concerning for us, right? And we'll see that whenever we have a change, the change doesn't happen at once. It takes time. And this is what we call the convergence. Anyway, so once again, when we look at the IP layer, we have multiple blocks. So we already talked about it, IP. We talked about ICMP. We talked about how we forward based on the table. But what we didn't discuss about is how do we create this table, the forwarding table. Whereas you may remember, we'll list the routes, giving all the destinations that we know. And basically, we can process the packets by matching the destination IP of the packet to the destination inside the table. We do a lookup, and we have the path. So this table is created because we are running routing protocols. And routing protocols are super important in networking. Why? Because they are using up to 80% of the CPU of a router is used because of running the protocols. So you see, so this is like one of the most critical tasks of a router. The other thing that we will see, so here we said that we need hundreds of nanoseconds to process the packets. So this is really fast. But to process here the events, which means that there's a change in the topology, how much time does it going to take to react and update the table? It may be up to a few milliseconds, even more sometimes. So you see the time scale is totally different here, okay? So we react to events up to a few milliseconds, even minutes, but the packets need to be processed in a couple of hundreds of nanoseconds. So that's the reason we're gonna see that usually we divide the routing with the forwarding. Anyway, so you remember that the problem that we have is like when we create a topology and we wire the routers together, what we try to do is to have as many redundancies as we want, right? We need to find one path is not enough. So why? Because we want to make sure that actually we can survive any link loss or whatever, or a router failure. We need to find a way to get around of the problem. The fastest is to provide multiple paths. But yet again, we can only use one. So which means that even though we have multiple paths, in IP, we can only do single path routing, which means that we don't divide the packet in two and make it take two paths. We don't load the balance, we don't balance the load on the two paths. There's only one. So which means that since we have multiple possibilities here, we need to make a selection. To make the selection, we do it usually by considering the distance. So actually the distance is not a way of doing something super optimal, so we cannot be optimal, right? We still need to find a way to rank the routes together. So the distance is a good way of doing this. But what do we mean by distance? Does it make any sense? Well, so that's the reason we need to define what do we mean. So anyway, so once we know the route, and you see that there are multiple possible ones have been selected, and that's thanks to that path that I put inside the table, that the routers can forward the packet by doing a lookup inside the table, such as for that destination, they can find the path that need to be followed, okay? And the decision is taken hop by hop, right? So it means that once we know the next one, the next one, the next one, and this way we get closer to the destination, which means that when we forward the packet, do we need to know the detail of the end path? No, the end-to-end path doesn't need to be known. The only thing that I need to know is who is the next hop. That's it. All right. Oops. So routing is really important because the way we're going to do the selection have multiple impacts here. And it depends on what is the point of view here. So let's start with the application, meaning the users. So obviously, the way we feel, the quality of experience we have when we use the internet, right, depends on how good is the path. So it means that since we have multiple choices, the choice that we make will basically match some of the requirements of the user and the application. So which means that a route may be good because it have a short delay. And this is good for voice. But if I try to download a huge file, then the throughput, the capacity is more important. Another one may be how much losses do I have on the path, all right? So you may see that the quality may be affected depending on which criteria am I using. And guess what? We already said that routing takes a lot of CPU. And right now, it uses 80% by using only one criteria. So the best would be to expect the router to compute multiple paths for one destination, giving the requirements. But we cannot do, because this is not scalable, it would be NP hard. So it means that it would be impossible because at some point you don't have enough CPU to do it. So since we cannot do it, given the scale of the internet, we only use one size fits all, one criteria, right? But at the end, we're still gonna have some problems depending on the application that I'm using. Sometimes I may not be happy because the delay is not good enough. Maybe the capacity is not good enough, and so on. So that's for the end user. So routing is very important for the end user. The other users, anyway, the other entity who is very impacted by this is the network operator. So the network operator is a guy who installs routers, put some links. So the cables are not there out of random, so you need to deploy them. So they cost money, not only to deploy, to roll out your network, but as well because you need to maintain them. So if it's broken, somebody needs to go fix it. So you see, so monthly you have a cost because you have links that you need to maintain. The maintenance is a huge cost here. So which means that at the end, what matters to the ISPs is to say that, okay, so I deploy 10 routers with hundreds of links. Am I using them? Maybe some of the links, because of routing, all the traffic goes on very specific areas of the network, and other ones are totally idle. Am I happy with this? No, I'm not. Because if I maintain links, it's for them to be used. So on the other side, so the operator wants to remove the hotspot where you're going to have a lot of congestion and make sure that you can spread and balance the traffic across your network. Okay, so maybe some traffic won't follow the shortest path, but it's going to avoid the congestion. So you see, so the network operator wants to make sure that actually you have efficient use of your resources here. All right, so this is the second point. And the third point is like whenever there's a failure, the topology change because a router is down or a link is down, you want to make sure that actually you can find a new path and that the convergence is fast. So which means that you don't want to lose too many packets by the time that you compute the new path. So it means that here you want to do a design, you want your routing protocol to converge as fast as possible. All right. So three here main reasons why routing is really important in network, right? Okay, so once again, we already talked about forwarding. So forwarding, it is just the fact that it's what we call the data plane. Why? Because here, what the routers are doing, they're receiving packets with data coming from users, and they need to forward those packets, right? So you need to do a lookup in the table, and you forward the packets. On the other side, we have routing, and routing is concerned with the control plane. So which means that we already said that in order to compute a path, you need to know the topology. To learn the topology, the routers, they talk to each other with a specific protocol, which is a routing protocol, in order to learn more information regarding the topology. So the routing protocol, the purpose of the routing protocol is only to create a topology such as the routers know the topology and can compute the shortest path. And so those things are totally separated. Those two actions are separated. For instance, why is it separated? So can you cite one type of packet which actually doesn't need routing? Only forwarding is important to those packets. Any example of packet that doesn't need routing? When you have broadcast, do you need a table? No, I said everywhere. So do you need to pay the price of the CPU? No, you don't need. But why we don't do broadcast? Because broadcast is going to create so much traffic on the network that actually is not scalable. But yeah, in the worst case scenario, you can say that it's CPU versus bandwidth. So what should I optimize? You see? So in our case, yeah, broadcast could be very easy, but we don't do it. Okay, so we need routing. But there are examples where actually routing. So it's to show you that you can forward without routing. So those are two different things. So if I look at the forwarding, so once again, the forwarding is done hop by hop, right? And so basically you need the routing protocols to give you a table. Based on the table, whenever a router is receiving a packet, right, you're going to be able to match the destination to one entry of the table and follow the packet, okay, knowing the interface or who is the next hop. So you can have either interface or next hop router, okay? The two are the same. So basically, the table result of using some algorithms in combination with the protocols, because the protocol is going to feed the algorithm with information related to the topology, such as the algorithm can run. All right, so regarding the path computation, I just want to make sure that actually, well, using a protocol is not the only way. You can also do static, which means that you can manually configure the route yourself. So sometimes that's what we may do. And the reason we do this is because, first of all, you have more control. What do I mean by that? You just don't let the protocol decide. And then you say, well, do I have any choice? No, the protocol tells us that we should use this path, so I have no other choice. In the case where I'm creating the route myself, I can decide what is a good route. And I can control this. The other thing is, when we look at the forwarding, yeah, you may create the route such as it's not only based on what is the destination. You may ask, well, what is the source? Maybe you want to say, oh, this packet is coming from there, so it should go this way. Well, when you do the routing protocols, they only decide knowing what is the destination. Is it good enough? Well, you have no choice. If I'm the one controlling the route, I can see the route as end-to-end between the source and the destination. And I may decide how the route should be decided, okay? So that's really different. Obviously, this doesn't scale because you can do it for a couple of routes, but if you have thousands of routes, creating the routes one by hand is almost impossible. And what is more, if one route fails, I need to calculate the route by myself and find a new one. So the convergence is super slow here. But now, if I use the routing protocol, so we already said that the routers are discussed together, they exchange some information, such as they can learn the topology. So it means that in that case, this is super fast, because whenever there's a change, you can inform everybody else, and that is much faster than when I need to do it by hand, right? It's scalable. Why? Because the software that I'm using have been designed such as they can process thousands of routes at the same time. So this is scalable, which I cannot do as a human, even using a script, right? I can do it for tens of them, but hundreds of thousands is impossible. But once again, those algorithms are super complex. It means that it's really hard to debug. So if something goes wrong for some reason, understanding the reason why the routing is bogus is really hard to basically troubleshoot. It uses a lot of CPU, a lot of bandwidth because the routers they discuss with each other. So that creates a lot of traffic, background traffic, which may not leave enough bandwidth for the users. And it uses a lot of memory because I need to store all the information regarding the topology, right? And the larger is the network, the more information I need to keep in memory, right? And basically, the only thing that I can do is decide upon a path depending only on its destination. I never look back and look, oh, this guy is coming from that source. Maybe I should make a different decision. No, we don't do that, right? We don't do. So usually, actually, there's not a good and a bad one. Both are valid, meaning that what you can see in the network, most of the time at the edge of the network, we do a lot of static. And the more you get in the core of the network, you do a lot of dynamic. So they are like a two level, okay? The edge, very simple. The core, you cannot really do that, right? Okay, so just to come back to the separation between the control plan and the data plan. So what do we have here? In the control plan, you have algorithm that need to run at each router. So each of them need to compute a path to make sure that actually the algorithms are almost independent, which means that the routers need to discuss together. So what I represent here in red is a routing protocol that actually let the routers exchange information together, such as they can learn the topology. Then out of this, you're going to output the routes that you're going to store in the forwarding table. And this is where you're going to do your forwarding. If I'm talking about it, is because nowadays we are introducing new type of architectures, including the centralized one, which means that people start saying, so why should I run the algorithm at each router? Maybe it should be better to define a controller, like a server, for a bunch of routers in my routing domain. This guy is going to be in charge of doing all the computation, all the dirty stuff, which is use a lot of CPU. And then all I do is I install the routes at the tables. And that's it. And so basically a lot of people think, and this is what they call SDN, and SDN is exactly about it. So it means that everything that relates to the control plan, such as routing, is done in a server. And the forwarding, you keep it at the routers where you just install the routes. So the reason for doing this, I mean, first of all, you need to understand that the routers, depending on who is the manufacturer, have different type of interface. So you don't configure the routers the same way, first. So which means that you need to define different type of commands depending on the router that you have. So that's a nightmare. So this way you may say that now everything is centralized here, so I don't really need to go configure the routers. So you make them virtual. If you ever heard of SDN, this is exactly what they try to do, right? So they centralize the control plan and you do only the forwarding of the routers, right? Anyway, so let's keep it with the standard way, which means that we have our distributed algorithms. So we have the algorithms. So typically here, what we do, we make the selection based on the shortest path, okay? And shortest doesn't mean anything, okay? We need to define what do we mean by shortest. This is really important, okay? So it's more about the best path. Usually it's based on the notion of distance. And either I use Dijkstra or Bellman-Ford, I need to know something about the topology. So the difference that we have between Dijkstra and Bellman-Ford is Dijkstra needs to know the exact complete topology of all the network. Bellman-Ford hopefully can only do that on a partial topology. So you don't need to know everything about the network. Few information is enough. So in order to learn those topologies, either total or partial, you need a protocol. And that's the reason you do the protocol. So the protocol doesn't compute a path, they're just going to feed the algorithms. So the initial state, the minimal information that need to be known to the routers are my direct neighbors. So somebody have to tell me who are my neighbors. There are other routers, right? But basically, there's no discovery here of my neighbors. Somebody need to configure the IP of those guys, all right? And I need to install them here. So I need to know who are my neighbors and what are the IPs of my neighbors, okay? If I'm using a cost, I need to also tell you what is the cost for each of them. So which means that, yes, the cost is not computed dynamically. It is set manually by the administrator. That's the way it is. So the cost is defined manually. And the state of the link, which means if it's up or if it's down. And we're going to see that the router needs to define the status of a link. So it works through a beaconing message that you send regularly to make sure that the router is still up or the link is not down, right? Once you have those informations, right, you basically need to share this information with your neighbors. And to share that information regarding my own neighbors or the cost or the status of the link, you need to define specific messages to this protocol, such as you can share the information with your neighbors. And that's it. Okay? So this is what the protocol will do. And thanks to what I learned through my neighbors, I can run my algorithms. Okay? So in the internet, as we say, so we do single path routing. So there's no multipath routing. So even though I may discover multiple paths to a given destination, usually we only use only one of those paths. So that's the reason I need to select only one of the routes. And the selection criteria, what we call also the routing policy that we use, is based on a distance, and we want to take the shortest path given that distance. So when we talk about Bellman-Ford, which is implemented by the protocol that we call RIP, we count the number of hops. When we use Dijkstra, which is implemented by the OSPF protocol, we use a cost for each of the links. That's it. And obviously, we need to worry about whenever there's a change in the topology, what should we do? When there's a change, so we need to inform everybody else about the fact that we lost a link is down, but the same happen as well if a link is back up again. So you see, so whenever it's a failure or recovery, the result is the same. So you don't need to think about, oh, I need to converge again only because bad things happen. But even when you lose a link or when you recover the link, the result is the same, right? You see, the pay to price is exactly the same because in both cases, those are changes. And so where there's a change, you need several things. You need to detect a change in the topology. So you need to know that the link is down or you have recovered the link. Then you need to propagate the change to your neighbors. Then you need to update to recompute the path, to remove the path from the table, recompute the path, and update the table again. And you see that this takes time. And during that time, you lose the original path. And so it means that during the period where you need to compute the path, what's going to happen? You're losing packets. You're not going to start to buffer the packets hoping that you're going to have a new route. If a packet arrives and you don't have the route available in the tables, what you to do, you discard the packet, and you may send an ICMP message, and you remember there's a message called the destination unreachable. You remember there's a specific message. This is the kind of message you use when your table doesn't have the right route. So you see, so that convergence can take a lot of time. And during that time, you're losing packets. And that's very expensive. So you want to minimize the time that it takes to update your table, giving a topology change. All right, so always keep in mind, whenever we talk about a routing protocol, we always need to keep in mind that actually the convergence is super expensive. Okay. So in the internet, we have two main approaches due to the fact that we have Dijkstra and Bellman-Ford. And so we need two specific protocols such as we can feed those algorithms. So the one is what we call the link state, and the other one is a distance vector. Two approaches. So in the link state, as indicated by the name, what we share with the neighbors is what we call the link state packet. So the link state packet is nothing more than a packet where for all the links that I have to my neighbors, I'm going to link the IP of my neighbor, the cost of that link, plus the status of the link. And I do that for all the links to my neighbors. So that's my packet. What do I do with this packet? I'm going to flout it everywhere in the network, such as everybody else can learn about those links to my neighbors. So let's say I have a network with 10 routers. How many messages am I flouting at the same time? If I have 10 routers, each of them need to flout their own link packet. Yeah, so we have 100. So can you believe how expensive it is? So you need to flout not only one, but as many times as routers that you have in the network. So this is super expensive, but how can I learn fast about any other link in the other side of the network? I have no other way, right? So I need to flout because I need to make it super fast because everybody needs to have the complete topology. So that topology will be maintained in what we call a database, and it is a link state database. So that database needs to have all the links in the network, including the cost of the link, plus the status of the link. Based on this database, this is what I'm going to feed to Dijkstra. I'm going to stuff Dijkstra with the database, such as that Dijkstra is going to start running and will output all the shortest path to all possible destinations in my network. All of them. So you see, so if I have 100 nodes, I have 100 of routes, right? So obviously here, the routing policy that is used depends on the cost. But once again, what is the value that I'm using for the cost? We already said that this is defined by my administrator. The routers don't decide on what is a good cost. No, it's the admin who needs manually to enter the cost. So it could be the value by default because the routers are installed with a default value. You may leave it this way if you're happy. But normally, serious admins, they're going to put some specific values, right? Because you may see that now, let's say I'm using OSPF, which is a link state. I'm not happy with the path. I can see that that path doesn't make any sense, or it creates a lot of congestion. Can I control routing? How can I do easily? Change the cost. You see, so that's super, super convenient, right? If I'm not happy, I'm going to put like a lower cost or a bigger cost in one link, such as I can change the route. And you see, so what we call it, you may have heard, when we do traffic engineering, it means defining for each of the links the good cost. But you know something? Hopefully for us, there's no algorithm which is not NP hard, which will give me the best cost. You know, I just give the topology, I give the traffic, I say, okay, give me what are the best values. There's no optimal way in a limited time period for a large network to give me the perfect values. Hopefully, it is NP hard. If you start running the algorithm, it may take a century for large networks. So we cannot do that, right? So we need to find heuristics to make it easy while achieving part of the objective. So we cannot be never optimal, but we may try to optimize few parts of the problem. Okay, and that's the reason we define what we call heuristics. You've heard of heuristics, right? This is an easy way to try to achieve the objective while being suboptimal, right? But we always consider how much time and how much CPU does it need, giving the result. So it's a balance, right? So we have easy ways of doing it. So protocols using this, there's OSPF, which is super famous, and the Cisco version of this one, which is ISIS. This is pretty much the same protocol, but ISIS is from Cisco, but it's doing link state. So it's very similar to what OSPF is doing. And nowadays, because of the possibility that I have, thanks to the cost, to adjust the routing to my liking, it's super popular. On the other side, what do I have? I have the distance vectoring. So here we don't send link state packets, but what I will do, I will list inside the message all the destination that I know, not my neighbors, all the destination that I know in my network with the distance of the path that I know for those destinations. And this is what we call a vector. So the vector gonna list all the destinations with, I put D, I'm sorry, with the not the cost, but the length of the path. So this is all I share. So I don't give any details. The only thing that I say is that I know about those destinations. This is how I can reach them. Do you like this route? You may use it. That's it. So basically, I don't flout, but I send it to my direct neighbors, my vector, who may update their own vectors and they share it with their own neighbors. So you see, so there's changes hop by hop that may update the final vectors. We're going to see more details about that. So basically, the Bellman-Ford algorithm is very simple. So we're going to see examples. So there's no routing policy. Why? Because unfortunately, the protocol that we have, which is RIP or RIPE, whatever you want to call it, actually RIP needs only calculate the distance based on the number of hops. So if I have like a distance of 3, it means that there are 3 routers before I can reach a given destination. So my question now is the following. So in OSPF, we saw that we can tweak the routing. In RIP, can we do anything about it? No, we cannot. So yeah, so you see why RIP actually is not very popular. And what is more, we're going to see that in the case of RIP, we have a big problem that you may have heard doing Bellman-Ford, which we call the count to infinity. We're going to see that issue, which is a very big problem with RIP. And that's the reason RIP is very slow when it takes to convert. So let's start with distance vectors. Okay, so once again, what we are sending here are distance vectors, okay, which include the list of destinations. And for each of those destinations, I'm going to put the distance. And in RIP, the distance, as I said, is expressed as the number of hops. How many hops do I need to go through? Okay, the distance is like by counting how many routers. All right. So the distance vectors are only sent to the direct neighbors, so it's not flouted. And you send it periodically or when your vector is changed. So if at some point you learn a new destination, you lose a route, or if the distance of the route is updated, you need to send again your vector. So either is event-based, like something changed, but if there's no change, you still need to do it periodically. Okay? Periodically meaning like every 30 to 60 seconds, for instance. Okay? All right. And so based on this information that I'm receiving in the vector, this is where I'm going to use Bellman-Ford algorithms. And once again, what I'm going to do, I'm going to process per destination. So for each destination that I learn, I will basically select the neighbor who actually advertised the shortest distance, as we already said. Okay? So the thing here is we have what we call the Bellman-Ford equation, which is here. So be careful, this is a very general formula, which actually accounts for the fact that you may have a cost. So what is interesting is actually Bellman-Ford can use a cost, but when we implemented using RIP, we say no need for cost. So that's really unfair to Bellman-Ford. But RIP, we put a cost of 1, and we cannot change that value. So basically, all we are saying here is the fact that when you have V, a given destination, which is Y, and I'm X, so if the vector have been advertised with the distance here, and here is the cost from X to V, my own distance to get there is the sum of both of them. Hopefully that works. Okay? So let's take that quick example here. So I'm U, and I'm trying to compute a path toward the destination Z. So you may see how many neighbors do U has? U has how many neighbors? Can you count with me? 3. Yes. We have X, we have Y, and we have double. And we're going to think about what is the cost that is actually sent regarding Z. So if I look at X, what is the distance of the shortest path to reach Z? 3? Yeah, that's what I think too. So I think that the slide is not good, but anyway. So this is the path known to Z. Let's see about Y. So what is the distance from Y to reach Z? The shortest one, 5, right? Because I can go here. I'm sorry, because yeah, it's a little 1 and 2, right? So I will advertise 5. Okay, and let's look at the last one. So which color should I put? Oh my God, let's put black maybe, or yellow. Yeah, yellow. So now regarding Y, what is the shortest distance to get to U? Yes, it is this one. And so this is 3. And so now be careful, because to go from U to W, it's 5. To go from U to W to Y is 2. And here is 1. So it means that U, if it goes through X, what is the final cost to reach Z? 3 plus 1, 4. U to go through Y to Z, what is the final cost? 5 plus 2, 7. And U to go to W to Z, what is the cost? We said that is 5, it's 8. So what is the shortest path that we can use? X. Because this is the best path. Is that okay? So it means that the shortest path should be this one. Yes. Okay? So that's it. So I'm receiving advertisements. This is how I learned about a route. I know nothing else regarding the route than the distance advertised by the neighbor, and I'm going to choose the closest one, okay? The one that gives me the better distance. Okay. So the algorithm is pretty simple, right? So once again, you maintain the cost to your neighbors. Whenever you receive the vector, you're going to maintain the distance vector giving all the possible paths that you have. So what is interesting as well is probably I didn't phrase it well. What you're going to maintain, it's only the neighbors that provide you the shortest distance. So even though you may learn like in the previous example, you see, I know all of them. These ones, I forget about them. I don't keep them in the memory. The only thing that I keep in my table is the shortest path. And so what it means that, let's say if at some point I lose that link here, what should I do in that case? So once again, I'm here, this is my shortest path to Z. For some reason, I lose the connection to X. If I'm using Bellman-Ford, what should I do? Yeah, so that's a good point. So you need to inform your neighbors, that's for sure. But regarding the path that you're going to use, first of all, you need to wait to discover, and that takes time. We will see that later. How much time does it take to see that it's down? Because it's not instant. Even when the link is down, you need to wait a little before you can discover that you lost the link. But do you have any other possible route that you can use? No, you are blind. If you lose that route, you have no other route because you forgot about what the other guys told you. So what you should wait? You should wait for the next update that's going to be received by your neighbors. And if the first one that you receive comes from W, which one are you going to use? W. And then maybe you're going to receive the one from Y, and maybe that's going to update your route, and you're going to lose the one to W, and you're going to go through Y. So you see, so the only way when you lose a route to be able to discover a new one is to wait for the next advertisement coming from your neighbors. Even though in the past they may told you that the route was available, you forgot about it. You have no memory of this because you only maintain the shortest one. Okay? All right, so you maintain this, and you send periodically, you send to your neighbors your own vector periodically. Okay. So basically, what I mean by that is, first of all, the routes need to be refreshed. So even if there's no change, you refresh. And then when you lose a route, you need to inform your neighbors, and then wait until you can recompute again the path. Right. So basically, it's a very iterative protocol, okay, which means that you have a loop where you keep waiting. You wait for what? You wait either for a local change or for a message from your neighbor. When you receive the vector from your neighbor, you check if it doesn't change your own table. So you check if you need to recompute the distance that you used to know. And if there's a change, because of that advertisement, you need to notify your own neighbors. So you see, so one change going to be propagated neighbors by neighbors until it reach all the network. You see? So basically you need one hop, recomputation, notification, recomputation, notification. So it's quite slow actually. When you cloud, it's very simple. You send everywhere, everybody update. So in that case, I need to wait until the notification arrived to me by having all the routers in the middle doing the recomputation and waiting for the update. So you see, that's a slow convergence. You can see that? So that is a little problem. So let's take an example here just to be able to explain another problem. So once again, at the beginning, so what I show you here is basically each of the routers, and I check what are the vectors that I'm receiving from my neighbors. So here for now, I haven't received anything from my neighbors. The only thing that I know is the available routes with my direct neighbors. So you see, so I know this route, 2 and 7, right? And to myself is 0. So then what's going to happen, I'm going to receive the vectors coming from Y and from Z. And in Z, going to inform me about this and this one about that. So you see, so what is happening here is the fact that thanks to the vector coming from Y, I'm going to realize that there's a better path that will let me reach Z with a cost now of 3. This is thanks to the update that I received from Y. Then the next time I'm going to share that information that I received from here. And actually now I know that to go, so Y will share the fact that he can go to X with the cost of 2. You send it to Z. And so Z will check that, oh, so the path that goes through Y have a cost of 3 instead of the 7. So let me update my table. Okay? So this is how you see by conversion to discover about the topology. But locally, the only thing that you know is what the information have been shared by your neighbors. Okay? All right, so this is RIP, and starting from this point, everything is stable. Maybe something will change in the future, but there's no way I can know about it. Okay? Final problem that we have and that I want to discuss about in a minute is, first of all, to see what is the implementation that we have. So we have RIP. So RIP, as we explained, so they have the vectors. So in RIP, we send them every 30 seconds if there's no events. So we refresh the vectors and we send them to our neighbors every 30 seconds. The cost of a link is always 1. A valid distance needs to be smaller than 16. Otherwise, it means that it's not reachable. And I will explain you why. All right. And basically, RIP is not very scalable. Okay. So one of the first questions that I have before I show you the count to infinity problem is, how can I discover that the link is down? Let's say I have A and B, they are connected. At some point, I lose the path, the link. How can A and B knows about this link failure? So what we do, we know that the DVs, the distance vectors, are sent every 30 seconds. So which means that if in 100 seconds we didn't receive any vectors, it means that the link is down. So how much time does it take? Up to how many minutes? That's a lot, right? That's a lot. 180? That's crazy. That's how slow is RIP. But as well, if I want to improve this, I need to improve this. In that case, I'm going to have too many vectors. So I need to keep it, right? Oops. So let's try to explain about the count to infinity problem. Okay? So let's look about it. So I have this quick network that I have here. After convergence, what do I have? To reach X, it's myself, is 0. To go to Y, I go through Y. And to Z, I need to go through Y with a cost of how much? Okay. Z have the same table. And Y have a table which is X, Y, Z, 2, Z, 1, and Y myself. All right, pretty standard, no problem. So let's say at some point, and I don't know in the example which one we're going to choose, but anyway, whatever, it works with any of the links. This one is down. So what's going to happen? After 180 seconds, I will realize that actually Z is not reachable anymore. And Y is not reachable anymore. Okay? And look, I'm not very lucky because by the time that I realize that I lose this, I receive the vector from Y. And in the vector, from X, X going to tell me that, oh, you know, I know how to read Z. I will say, fine, I lost the path. So you're giving me a path. Let me put the new value. So what should be the value now here? It was 2 here, but just anyway. So add in. Yeah. Okay. All right. But that's a fake path, right? And now I'm going to send my own update telling that it's 5. So I'm going to update this one. Well, what should I put here? If now Y is telling me that it takes me 5, 7. And so then I'm going to send a new vector. What is the new value here? 7, 9, 11, 13, 15, 17, 19, and so on. And you see that you have a forwarding loop, because in order to go to Z, I go to X, who go to Y, who go to X, so I have a loop. And there's no way to break that loop. And the only way that we found at the beginning is to say that, okay, you know something, if you reach the value 16 here, it means that something is bugged about the route. So if you have 16, forget about it. It means that there's something wrong. So please refrain from trying to join Z. So this is what we mean by we limit the infinite. We put 16. So 16 is kind of, you reach that value, you're dead. Something is wrong. Okay? But it means that still you need to wait until it reaches 16 to realize that something is wrong. And it takes time. And at that point, you have a loop. So we try to improve the things. And the thing that we did is we realized that actually what was wrong here is the fact that when I lose this and this guy gives me a route with a cost of 3, that route is somehow a fraud. Why? Because the route, who have talked X about this route? Y. So basically, X is telling me an information that I'm supposed to know, and he's giving me a second-hand information. So what should I do? So we have first what we call the split origin. And we tell to X, you know something? For the routes that you learn through a neighbor, you never advertise that route to that neighbor. So you're going to send your vector removing all the routes that you learn through that neighbor. So this is a split origin. But we realize that that is not good enough because we still can have some loops. And so a better way of doing this, we allow X to send the vector with Z, but what is the cost that we're going to put here in order to make sure that Y will never use that route? Yeah. So this is what we call the Poisson reverse. So you see, so because of the count to infinity, first, we limit the infinite with 16. Then we started doing split origins, but it was not good enough. So now, most of the time, we do Poisson reverse. But still, the convergence is really slow. Okay, so you understand those 3 measures? All right? So that's what is shown here. So anyway, guys, so once again, so link failures, you discover them through using that timer. So it takes a lot of time to realize about it, right? And basically, normally, we have the Poisson reverse with the infinite distance of 16 to be able to limit the count to infinity problem. So this is what RIP is doing. But once again, RIP, because you have no control about over the routes. And basically, you still have the problem of convergence is not very popular anymore. So we keep it for rather very small networks. And most of the time, we use OSPF. And OSPF, this is what we're going to study next week.